Okay, let's dive right into this fascinating journey where we're going to unpack the invisible mechanics of waves. We'll see how they govern literally everything, from the water ripples in a pond to the very light hitting your eyes right now. Whether it's the sound of my voice, the screen you're looking at, or even the tremors of an earthquake, they all follow this beautifully consistent set of rules. And in this explainer, we're going to break down those exact rules using some really elegant visual models. Oh, and real quick, if you want to master topics exactly like this, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Okay, let's get into it.
Here's our roadmap for today. We're covering energy without matter, the anatomy of a wave, ripple tank revelations, the rules of reflection, and finally, bending reality with refraction. We'll start with the broad, observable rules of physical waves, and then we'll apply those exact same rules to the high-speed, invisible world of light.
All right, Section 1, Energy without matter. To really understand waves, we first have to fundamentally shift how we think about movement. Usually, when energy moves from point A to point B, we think of a physical object physically traveling that distance, like a baseball being thrown. But waves are entirely different. The crucial takeaway here is that a wave is a disturbance that carries energy from one place to another, but it leaves the actual material exactly where it started. Think about a leaf resting on a still pond. If you drop a stone nearby, the ripples spread outward, right? But if you watch that leaf, it just bobs up and down as the ripple passes under it. The water itself isn't rushing outward, only the energy of the disturbance is.
Moving on to Section 2, let's look at the anatomy of a wave and see how this energy transfer builds into a physical structure.
Because the material itself isn't traveling with the way the particles vibrate gives us two very distinct categories of wave motion. First up, we've got transverse waves. Imagine tying a rope to a wall and just flicking your hand up and down. The wave travels horizontally toward the wall, but the rope itself is moving vertically at right angles to the direction it's traveling. Water waves and light waves, they are both transverse. On the flip side, we have longitudinal waves. Here, the particles vibrate parallel to the direction of travel. If you take a stretched spring and push and pull it sharply, you'll see these tight compressions and loose rarefactions traveling down its length. That's exactly how sound waves work.
Now, this brings us to a brilliant universal mathematical rule, the wave equation. This applies to all types of waves, from slow ocean ripples to super fast light waves. If you want to figure out how fast a wave is traveling, you just need two pieces of info. First, it's frequency, which is how many complete waves happen per second, measured in hertz. Second, the wavelength. That's the actual physical distance between two successive crests, represented by the Greek letter lambda. You just multiply those two numbers together, and boom, you get your wave speed. It's v equals f times lambda. Simple, elegant, and it works every single time.
Okay, Section 3, Ripple Tank Revelations. Abstract math is great, but it's really cool when we can visualize these properties in the real world.
To actually study this stuff practically, physicists use something called a ripple tank. It's basically a shallow, clear tray of water with a light shining from above, which projects the shadows of the water waves onto a screen underneath. By hooking up a motor to a little bar that just taps the surface of the water, we can generate these perfect, continuous straight ripples. And here's the really clever part. To measure the exact distance between these crests, which we call wavefronts, scientists use a spinning disk with slits in it called a stroboscope. It creates a strobe light effect that essentially freezes the continuous ripples in place on the screen, making them super easy to measure.
Now check this out. This is a phenomenon called diffraction, and it's absolutely fascinating. It shows how the physical width of a gap entirely dictates the shape of a wave as it passes through. Look at the left side. We have a narrow gap, about the same size as the wavelength itself. When the straight waves hit that barrier, they squeeze through and spread out into these perfect semicircles. But look at the right side. When the gap is much wider than the wavelength, the wave pretty much just marches straight on through, only curving a tiny bit at the very edges. This isn't just a neat trick. Engineers literally study this in ripple tanks when they're designing harbors, so they know exactly how ocean waves will spread around seawalls.
Let's look at another wild phenomenon, interference. What actually happens when two waves crash into each other? Well, they don't bounce off like billiard balls. They pass right through each other and combine their effects. If two wave crests arrive at the exact same spot at the exact same time, they join forces to make a much bigger wave. We say they are in phase. But if a crest from one wave arrives at the exact same time as a trough from another wave, they perfectly cancel each other out.
It leaves the water completely flat and undisturbed. You can actually see these distinct, blurred lines of flat water radiating outward in the interference pattern right here.
That brings us to Section 4, the rules of reflection. We're going to transition from the slow, mechanical waves of water to the ultra-fast electromagnetic waves of light. And before we do, just a quick reminder, subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. Let's see how light obeys these exact same principles.
First things first, we need to establish how light physically moves. When you see sunbeams streaming through the dust in a forest, like in this really striking image, you're seeing perfect visual evidence that light travels in straight lines. We call the path of that straight line a ray, and a whole stream of light is a beam. Because light travels in these highly predictable straight paths, it means we can precisely manipulate where it goes using reflective surfaces.
And controlling light relies on one unbreakable geometric rule, the law of reflection. Imagine drawing a line perfectly perpendicular to a mirror. We call that imaginary line the normal. The angle at which an incoming light ray strikes the mirror relative to that normal line is exactly 100% equal to the angle at which it bounces off. It doesn't matter if you're dealing with a calm pond, a barrier in a ripple tank, or a piece of silvered glass. The geometry of a bouncing wave is always perfectly symmetrical. And we can use that exact symmetry to our advantage. Just think about simple periscopes, like the ones people use to see over a crowd. By placing two flat plane mirrors parallel to each other inside a tube, but angled at exactly 45 degrees, we are totally exploiting the law of reflection. The light from the environment hits that top mirror, turns exactly 90 degrees straight down the tube, hits the bottom mirror, and turns another 90 degrees directly into your eyes. It is such a brilliant, simple way to see over a tall obstacle, just by predicting how the light wave will bounce.
Now, it's really vital to understand what kind of image a mirror is actually creating, because there's a huge difference between a real image and a virtual image. A real image, like what forms inside a pinhole camera, is made by actual light rays converging, meaning you can physically project it onto a piece of paper or a screen. But when you look into a mirror, you're seeing a virtual image. The light rays are bouncing off the glass and into your eyes, but your brain always assumes that light has traveled in a perfectly straight line, so your brain gets tricked. It thinks the rays are coming from an intersection behind the glass. You can't put a screen behind your bathroom mirror to catch a reflection, right? Because the light isn't physically back there.
All right, Section 5, Bending Reality with Refraction. Let's dive into our final wave phenomenon, which happens when a wave passes through a boundary and actually changes its speed. This is where reality gets a little bent.
I'm sure you've noticed this at some point. If you drop a coin into a swimming pool, the water always looks deceptively shallow. Or if you're standing in the shallow end, your legs look strangely short and stubby. The answer to this everyday optical illusion lies entirely in the physics of a wave changing mediums, and we call this process refraction.
Take a look at this pencil in a glass of water. It looks like it's been physically snapped in half right at the waterline. Here is exactly what's happening. Light travels slower in denser water than it does in the lighter air. So as the light rays traveling from the underwater tip of the pencil cross that boundary into the air, they suddenly speed up. And this abrupt change in speed causes the rays to physically bend away from our imaginary normal line. Just like with the mirror we talked about, your eye traces those bent rays backward in a straight line, which creates a virtual image of the pencil tip that sits much higher than the actual physical pencil.
But why, fundamentally, does a change in speed cause the wave to bend its direction? Our source material has this absolutely brilliant analogy for it. Imagine a row of 3 people marching arm in arm on a solid paved road. They approach a muddy, marshy field, but they hit it at an angle. The person on the far end hits the mud first and gets bogged down, slowing down immediately. But the other 2 are still walking at normal speed on the pavement. Because they're linked together, the whole line naturally swings around and changes direction as they enter the mud. A wave front of light does the exact same thing when it hits a denser, slower medium at an angle. It swings round.
To really put this into perspective, let's talk about the speed of light. 300,000 kilometers per second. That is the staggering speed of light in a vacuum. It's literally the cosmic speed limit. But, remarkably, when light slams into a solid block of glass, it slows way down to just 200,000 kilometers per second. It loses a third of its speed. That massive drop is exactly what causes the dramatic bending or swinging of the light ray that we see. Physicists actually quantify this slowing effect using something called the refractive index, and it's a super straightforward calculation. You just take the speed of light in a vacuum and you divide it by the speed of light in whatever material you're studying. So for glass, 300,000 divided by 200,000 gives us a refractive index of 1.5. This little bit of math gives us a crucial ratio, telling us exactly how severely a specific material is going to bend light. Basically, the higher the number, the slower the light travels, and the sharper it bends.
And that brings us to the end of our explainer today. By understanding how waves transfer energy without moving matter, and by mastering these really foundational rules of reflection and refraction, we've been able to manipulate the universe in some truly incredible ways. I mean, it's exactly this science that allows engineers to bounce lasers through tiny glass optical fibers, literally carrying the internet across the bottom of the ocean. So, what other invisible boundaries of reality might we learn to bend next? Something to think about. Before you go, remember to subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Keep exploring, and I'll catch you next time.